as a vital person in your company or in whatever you're working on. And so our plan in these sessions is to mix theory with hands-on labs. We plan to give you both the fundamental understanding that helps you learn things later on on your own, and at the same time we want to give you a sense of how it is to apply these concepts. Okay? And so today we're gonna go over an introduction to AI and machine learning. We're gonna cover some of these other bullets before. These slides are from last year, so we've moved things around a bit. So first of all, what is AI and what is machine learning? So AI is this big umbrella term that kind of comprises of different things. Machine learning is a subset of AI. So AI is any system that simulates human intelligence. Machine learning specifically simulates the learning aspect of human intelligence. So whenever you have a machine where you give it some data and it learns from that data so that it can later on make decisions, this is when you're talking about machine learning. Not all of AI is like this. Okay? So to give you an example, there are AI systems, for example, that play tic-tac-toe or XO. And the way they play it is by just running a very big computationally expensive simulation, like think ahead until the end of the game, and try every possible move and then choose the best one. So this doesn't really involve any learning. The model is not learning anything, but there is some intelligence. So simulating these games and trying every combination, that requires some level of intelligence. Again, these are not very well-defined words, but this is an example of an AI agent that doesn't involve machine learning. Okay? So the point I'm trying to make is machine learning is the subset of AI. It's not the entirety of AI. And even machine learning is divided into different fields. So we have supervised learning, unsupervised learning, and reinforcement learning. We're going to go over these again in a bit. And there's also deep learning, which we're going to cover at some point later on, which kind of intersects with all of the other fields. So machine learning, this is one of the main takeaways from this session. Machine learning is split into three large fields. We have supervised learning, unsupervised learning, and reinforcement learning. Okay? And supervised learning is also divided into different fields. I'm not gonna go deeply into what the other field is, but today we're gonna have a long discussion on regression. Okay? So machine learning is divided into three large sub-areas, if you want. Supervised learning, unsupervised learning, reinforcement learning. And we're gonna discuss what each of these means in a bit. And supervised learning is divided also into different subparts. One of them is regression, which we're gonna cover today. So what is supervised learning? Supervised learning is the type of machine learning where you have a bunch of labeled data and you give it to the model, and the model learns to predict the label based on the input features. To elaborate, let's explain this through an example actually. Let's say you want to build a spam detection email system. So I receive an email, I want to classify it as either spam or not spam. So I get a bunch of data, a bunch of emails, and I manually label every single email as either spam or non-spam. Then I give this to my model, and the model learns to predict the label based on whatever the text in the email is. And the key characteristic here is that I've actually labeled every email in the dataset. So the model kind of has, it's kind of like how you study for exams, you solve the previous exam. So you have the previous exam and the answer key. And so you try to solve the previous exam, you do your best, and then you compare your answers with the answer key. If you didn't have the answer key, you wouldn't be able to apply this type of learning. Okay? So the key characteristic in supervised learning is that my data set is labeled. I know the output for every input in my data set. Unsupervised learning, on the other hand, I don't really have an answer key. I have a bunch of data, and I'm trying to, for example, find clusters in these data. So I'm trying to find relationships between my data points without really having a specific label to predict. So I'm not trying to predict specifically if this email is spam or not spam. I'm trying to kind of group these emails together. So in a sense, these emails, they're kind of related. Maybe they're sent by the same person, maybe they relate to the same genre, but these emails are related. Okay? So there isn't really a specific label I'm trying to get. There's just some notion of these are related together. Maybe I'm not trying to predict clusters, maybe I'm trying to predict anomalies. So this email is a weird email. I don't know how exactly it's weird, but I know it doesn't belong to the rest. And notice the difference between supervised and unsupervised learning is that in supervised learning, I have a specific label I'm trying to predict. I'm trying to predict whether an email is a spam email or not. And unsupervised learning, there isn't a specific output label, but I'm trying to tell in general what trends can I find in my data set. Okay? These are some examples of unsupervised learning. When it comes to reinforcement learning is another approach. It's basically when you have this agent and you allow it to make any move at once. So let's say you're playing a game, maybe you're not playing a game, maybe you're trying to teach a robot how to move. So you allow the motors to do anything, and then based on the result, you either reward it positively or negatively. And a reward is just a number. And so the agent now learns that I want to maximize my number. So when it does a good move, you would give it a positive reward. When it does a bad move, you give it a negative reward. And it doesn't really understand what it's doing. The robot doesn't understand that it's walking, but it understands that I'm trying to maximize my reward. And so it ends up doing more positive moves or more good moves because by nature of how we've structured the reward function, if it tries to maximize the reward, it's going to end up doing good moves. Does this make sense? Does the difference between the three subfields make sense? Specifically between supervised and unsupervised learning. So one thing I want to stress is that in my actual data set, so when I get some data and I want to train my model, in supervised learning, this data set would be labeled usually. In unsupervised learning, it usually would not be labeled. Labeled means that there is a specific column that I call the label, and this label is my output. Okay?
سؤال
تفضل.
بالreinforcement learning ما في training صح؟ إنه أنت بتتركه.
ما في training. Okay. I should have clarified this. اللي بيصير بالأول أنت بتتركه يعمل اللي بده إياه. Okay? Then gradually, okay. So it's making random moves, let's say initially, but then for every move it makes, at some point it gets a reward, right? So gradually it will learn that these moves give me positive rewards and these moves give me negative rewards. So there's this sense in learning which move gives me a positive reward by trying things. يعني, let me give you an example. Let's stick to the example of a robot trying to walk. Let's say it moves its motors in some way, and so it falls to its side. You give it a negative reward for that. Notice that you don't really care what the motors did, you care about the result. I care that the robot toppled over. I don't care what it did exactly, but it fell to the ground, so I give it a negative reward. The reward can be based purely on the result. You don't really have to understand what happened. You don't always have to understand what exactly happened in the details. So you fell off, I give you a negative reward. You were able, for example, to move 1 meter forward, I give you 1 point of positive reward. You were able to move 10 meters forward, I give you 10 points. So this is how the reward function would be structured. And initially it would be making dumb moves, it would keep falling over. But at some point it would learn, okay, so if I do this combination of motor movements, I would not fall over and I would get a positive reward. So there's this gradual learning process. Does this answer your question? Okay. So yeah, today our focus is, we're gonna forget about these for today. Like, remember what they mean, but we're not gonna focus on them. We're focusing on supervised learning, specifically regression, and we're gonna learn the first regression algorithm in this series, which is linear regression. So what is linear regression? The setting of the problem is this. So I have a bunch of data points, and I'm gonna plot them on a scatter plot. What's a scatter plot? We're gonna see this a lot. A scatter plot is basically the x-axis and y-axis each, okay, the x-axis would represent my input. So in this case, I'm trying to predict the average hotel price as a function of the number of tourists. So if I get this many tourists, then the average hotel price would be this. Okay? If I get this many tourists, then the average hotel price would be some other number, whatever. So the problem I'm trying to solve is, if next year I predict, let's say, this many tourists, I don't have a specific data point for this amount of tourists, but I want to predict what would be the average hotel price, okay? And if you notice, the output here is a continuous number. The output could be any real number. And this is one of the characteristics of regression. So when we're talking about supervised learning, we said that a characteristic of supervised learning, as opposed to unsupervised or reinforcement learning, is that the data set is labeled. Now, when we're talking about regression versus classification, as we will learn later on, in regression, we're talking about an output that could be any real number. Later on, we're going to see that this is not always the case. For example, when I'm trying to classify things, like I have a picture of a person, and when I tell if this is a male or a female, the output cannot be 0.5. It's either 0 or 1, either male or female. So this would be a completely different type of problem. But when we're talking about a problem where the output can be any number from a continuous set, then we're talking about regression. So again, what we're trying to do is, if one day I get this many tourists, I want to predict what the average hotel price would be. Can anyone make like an approximate prediction here? If I get, this would be in thousands, so this is 12.5 million tourists. What do you think the average hotel price would be approximately?
95.
Okay, so how did you get this number? Exactly. So the general trend is this way, right? So the more tourists I get, the higher the average price would be, right? And so if I try to follow this trend, then approximately I would end up somewhere here, which is 95. Okay. This is what we're going to try to do. We're going to try to design an algorithm that does exactly this. Okay. And the way we're going to do this is we're going to try to find the line of best fit. What's the line of best fit? It's the line that most closely resembles my data set. So the general trend here is that the more tourists I have, the higher the average price. And this is what my line is trying to represent. This is the direction my line is going in. Did you all get an intuitive understanding of what the best fit line is, or line of best fit? Okay. So I'm starting with this scatter plot, and I want to get to this line. How do I do this? I'm going to start with some random line. Just throw out any line, and we're going to try to gradually improve it. We started with this obviously bad line because it's underestimating all of my data points. This is obviously a very bad line, but gradually I'm going to move it up. I'm going to move it up until I get my line of best fit. So again, the way we're doing this is we're going to start with a random line, improve it some more until we get to the line of best fit. Okay? And you might be wondering if there's a way to just mathematically get the line of best fit. Maybe you've even seen it before. You can mathematically find the line of best fit without going through these multiple iterations of improvement, but doing this is computationally expensive. So trying to do this the mathematical formula would involve a lot of computationally expensive operations that you can handle when your problem is this simple. But whenever you get to a problem with maybe more data points, more features, then things start to get messy. We're going to talk about this in a minute. It's going to make sense later on. But for now, just imagine the mathematical way doesn't exist, and we're going to motivate why this way is actually desirable later on. So what are some applications of linear regression? Maybe I'm trying to predict the price of a house based on its area. I'm trying to predict a car's fuel consumption based on its weight and engine size. I'm trying to predict crop yield based on whatever fertilizer or whatever chemicals are used in a specific agricultural area. So there are a lot of applications for regression, and we're going to start from here. my regression model, my linear regression model, is simply a straight line. Y equal ax plus b. And in the context of machine learning, usually we call this the weight, so we call it W, and this the bias, B. Okay? So this is my model. Notice how I have this hat here. Y hat means this is my prediction for the output. So X is my input, which in our example, what would the input be? In this example?
Number of tourists.
The number of tourists. And the output would be the average local price, right? So Y hat is my predicted output. So if I give you this input, my model will give me this predicted output. Okay? W and B are they're what's gonna drive the predicted output. So my predicted output is controlled by W and B. So what I'm trying to stress here is you can't control X. X is whatever the number of tourists is. You don't have control over that. What you have control over that as a machine learning engineer is these weights, is the weight and bias. Okay, sometimes we call this also weight, and so these are the weights of my model. Okay, or the weight and bias. These are the ways people refer to these numbers. So when I say Y hat is WX plus V, my goal is to make Y hat as close as possible to the Y's over here, right? And we don't know what as close as possible means yet, but we're gonna get there. So my goal is to train these two. When I say I'm training my linear regression model, it means I'm finding the best values of W and B. Okay? And the way I'm gonna do this is, we said we're gonna start with some random initialization. So we're just okay, so this is a random guess of what the line should be. And then I want to improve it. Usually when you want to improve something, you have to create some system in which you know how good that thing is. So if I'm trying to improve this line, I need to create a way to tell how good is this line? How much should it be improved, right? So who can think of a way that we can numerically represent how good this line is or how bad this line is?
حسب قد ايه it predicts well a known value.
Okay, what would the exact formula be? So if I give you this line and I tell you which line is better, this or this?
Yes.
This one. So what number would you assign to this and what number would you assign to this? I want some system in which we can assign numbers to a line and say this, like the badness of this line is 100, the badness of this line is 20, so this is better. Okay?
The difference between the predicted.
Exactly. I can go over every x value and check for this x value, the line would predict this y value, but the actual y value is this. So there's a large difference in y values. And then I can do the same for this. I predicted this y, but the actual y is this. I can do the same for this, and so on. Okay? And I get all these differences, and then what do I do?
Sum.
I can sum them, exactly. So I can just get these differences and sum them. But what happens, for example, in this case, when I have, actually let me do this is better. In this case, the difference is positive, let's say, because the actual output is higher than the predicted output. But in this case, it's negative. Do I care about the sign in this context? No, because it's kind of like I only care about the distance. And so what we're actually building up is we want to go over every data point and sum up the absolute value of the difference between the expected output and the actual output, right? But then, for convenience, instead of taking the absolute value, we're going to take the square, because we're going to be doing derivatives with this function later on. So taking the derivative of the absolute value is a bit more complicated than taking the derivative of square. Okay, and so the function we're going to end up with is this. It's a function of y hat and y. The subscript here means it's the ith data point. So for example, here I would be 1, I2, I3, I4, I5, I6. And so I is just a numbering of the data points. And what I'm doing is, I'm defining a function of y hat of I and y I, and it's the difference, and it's the square of the difference. And I'm gonna call this my loss function. This function represents how bad my model is for one specific data point. Okay? And as we've said, to get the cost function over all of my data points, it's gonna be a function, it's gonna be the average of this. We can take the sum, but what we're doing here is we're taking the average. The reason we don't want to take the sum is because then if you have more data points, then you would be penalizing the model more, right? So if usually you wouldn't change the number of data points while comparing models, but if you are, then if you have a model that was trained on 10 data points versus 100 data points, the one with 100 data points might be better, but the sum would be larger, just because there's more data points. So we're taking the average. We're also dividing this by half, also because when we take the derivative, this is gonna cancel out. So basically what we're doing here, you can ignore the 2, by the way. In some references, it's not even there. So you can say we're taking the average of this. And we define this as what? As the loss function. So the average of the loss function is the cost function. Okay? Sometimes we include this too, sometimes we don't. It doesn't really matter, because at the end of the day, if one model is 100 and the other is 50, or versus a model is 50 and the other is 25, still we can say the second one has twice as better of a score, right? So if everything is divided by 2, it doesn't really matter. So I'm summing the loss over all of my over all of my data points, and here I'm just writing this in expanded form. So what is y hat of I? As we've defined initially, my predicted output is just the output of this straight line. So the straight line is gonna be substituted here. It's w xi plus b. Xi is the input for the ith data point. So let's make sure we all understand this.
What is the n? The n, what is it?
N is the number of data points. And n is the number of points I have here. Okay? So again, a quick recap. My model is this straight line, wx plus b. Again, I really want to stress that I can only control w and b. I can't improve the model by changing x. X is not under my control. I have this loss function, which represents how bad my model is with respect to one specific data point. And then I have this cost function, which is the average of the loss over all of the data points. Okay? And notice that the cost function is a function of what? W and B. So you can't change yi, for example. You can't change xi. You can't change y hat directly by changing xi. You only have control over w and b. This is basically the heart and soul of your model. This is how you improve your model. You improve your w and b. So for example, if I want to send you this model, I would literally just send you w and b. Right? W and B are what define my model. I don't need anything more than that. And now we're gonna move on to this process where we're gradually improving the line. How do I gradually improve my line? I have my model, I have my cost function, so I know this line is bad, this line is good. How can I improve my model? هذا فيكم مع قلم لوح باي ذا واي؟ معك قلم لوح؟ Can you check مع هوني على اليمين؟ Please. Okay. So how can I improve this?
تتغير W B لتصغر الكوست فانكشن.
كيف بدي أغيرها؟ Randomly? We can just do it randomly. نجرب نغير ال W شوي، نجرب نغير ال B شوي، شوف شو بيصير. Okay. Any other suggestions? بلكي إنه try a bunch of random W's and B's. شوف احسن واحد مثلا بس انه there's okay بس I want to ask about your background. I should have done this at the start. بس شو الميجرز تاعونكم what year are you؟ بلشوا من يمين لشمال.
كمبيوتر ساينس جونيور.
اوكي.
CC. أول سنة.
اوكي.
Computer Science sophomore.
اوكي.
CCE.
يعني كلكم ماخدين 201 maybe math 201.
Yes.
Okay. Okay, this is gonna get slightly easier, but we're not gonna really go into a lot of math. بس نقدر نشوف إذا في قلم and this is I can explain this much better بالقلم. Actually خليني نشوف إذا في يفتح تاني. Okay. Okay. Let's do this. طيب. Hello, for now, let's ignore B. Let's assume B is 0, for example, or B is some fixed value. Okay? I'm trying to improve my model. How can I improve my model? What can I change to improve my model?
Is a
W.
prefix W.
W, exactly. So now, J is a function of W, right? And that's for now. Oh, actually, خلينا. Okay, so J is a function of W. And for now, let's say J looks something like this when I graph it. Okay. It's obvious that this point is lower than this point, huh? Okay. And if I choose W equal to, let's say, this value, let's call this 3, I don't know. Then I would end up at this point in my cost function, right? So I'm at this point in my cost function. Where do I want to go? I want to go lower, right? Do you remember what a gradient is from Math 101?
So
fx I plus.
So yeah, exactly. Gradient is I care about it geometrically here. So the gradient is a vector that points in the direction of most rapid increase, right? So the gradient in this case would point in this direction. Okay? So my gradient vector would point to the right. So if my gradient will always point in the direction of increase, what should I do? Just move in the opposite direction. If you're trying to decrease, if you're trying to get to a lower point in your function, then just always move in the opposite direction as your gradient. Okay? So what I'm gonna do is I'm gonna change W slightly, but I'm not gonna change it randomly. I'm gonna change it in that direction. So I'm gonna make W, for example, 2.9 instead of 3. Okay? Then I do this again and again and again until I reach this minimum point. Tamam? And this is how the gradual improvement in the line happens. I start at a random point in my cost curve, and then gradually I get to the minimum of that curve. Okay? But what's the problem here?
There's a lower point than.
Exactly, there's a lower point, and I couldn't reach that. And I can't reach that using this process. So if I'm always going in the direction where the function decreases, I will never reach the other point, the other lower point, right? And this is one of the downsides of gradient descent. But it can't guarantee to get me the lowest point because it's very sensitive, it's very dependent on where I start my process. Okay? So if I started here, then I'd be good. I'd find my lowest point. If I start here, I'd be cooked. I can't find it. I'd find this other lower point, this other low point. So I think you can all imagine how I would implement this. And I would just get the derivative of the cost function. How do I get the derivative? I can mathematically I can do the math. I go back to this. This is the derivative. So it's this big ugly expression, but we don't really care about what it is. Our point is the derivative of J with respect to W is something. Okay? And it's something where we have to sum over all the data points. Okay? But it's a derivative. I don't really care. So if you tell me my W is let's say 5, I can get you the derivative. I just plug in here. These are all constants. I know what my xi and yi are. They're in my data set, right? So I just plug in my w. For now, we said we're ignoring the v. So just plug in the w, and you can find the derivative. So I can find the derivative. Okay, but this problem where I have multiple minima, luckily we don't have to worry about that. The reason is, in the case of linear regression specifically, you can prove that the cost function looks something like this. It's parabolic. And where does this come from? You're summing a bunch of squares. You're summing parabolas. You're gonna get a parabola, right? So if this is 0, this is literally a quadratic equation in W. These are constants. This is a quadratic equation, and if you're summing quadratics, you're gonna get a quadratic. And the quadratic looks like this on the graph. So I don't have multiple minimum points. This is very convenient because now I'm guaranteed that gradient descent will find me the best point. I'm guaranteed that, okay? Or at least it's gonna get very close. طيب. So what I'm gonna do is, if currently I have a weight of WT, so at time t, my W is WT. At the tth iteration of gradient descent, my weight is WT. How do I find WT plus 1? How would I calculate that? Based on what we've discussed here.
يعني قصدك إنه عكس الجريدينت؟
صح، إنه عندي WT، نحن قلنا إنه إذا عندي W معين I will move it slightly، ما هيك؟ يعني واضح إنه WT plus 1 is dependent on WT. حبلش إنه WT بغير فيها شوي. فأوكي WT plus 1 WT plus 1 is equal to WT plus some modification, صح? What's the modification gonna be? إذا الجريدينت كانت G مثلا, it's the W component of G, صح؟ يعني جبت الجريدينت، شوف لي in which direction it's pointing، بس ما بدي امشي معه، بدي امشي عكسه. شو لازم اعمل؟ ماينس. So بدل بلس حتكون ماينس. Okay? So WT plus 1, the new value of W is gonna be the old value of W minus the gradient. ليش minus the gradient? I don't really care about the value of the gradient هون، بس اللي بدي وصله هو the direction of the gradient. يعني إذا الجريدينت okay. At this point the gradient positive or the W component of the gradient positive or negative? Positive. The W component of the gradient is positive. فإذا بعمل minus something positive شو بيصير بالW؟ WT plus 1 حتكون أقل من WT، حتكون زحت هيك، which is perfect. والعكس صحيح، إذا كنت هون the gradient will be pointing this way، شو بيكون؟ negative. So I'm doing minus something negative, so I'm adding to W. فدايما this works out. Okay? هلا it turns out إنه كثير مرات بنشوف this extra factor here. بيكون هون minus alpha G sub W بدل just G sub W. Alpha here is called the learning rate. This is a very important concept you're going to see in you're going to keep seeing the learning rate. The learning rate is a scalar value, it's a real number, that controls how sensitive your model is to new information. So if I'm standing at this point, and I'm going to move in the opposite direction of the gradient. We've agreed on that. But how big should your step be? So should you jump by a large step, or maybe you jumped a step that's too large and you end up here? Maybe it's too small and you take forever to go downhill. So alpha controls that value. Alpha controls your step size. Alpha controls how sensitive you are to new information. What I mean by that is, when you're standing here and you calculate your gradient is new information. Now I know how bad my model is doing based on my data set. And so this new information that I gain, how much am I going to use it? How much am I going to be affected by it? Alpha controls that. And usually alpha is a very small number, like 0.01 or 0.001. Okay? So what we end up with is this. Does this make sense to everyone? هل عنده سؤال على هاي؟ Okay. Well, I'm gonna go back to this slide. Things should be شوي clear. Wt plus 1 is Wt minus alpha, and this is the partial derivative of J. This is the W component of the gradient. I don't care about partial derivatives for today. W component of the gradient. B is gonna follow the same exact process. T plus 1 is Bt minus alpha, B component of the gradient. Okay? هلا if I want to bring B into the equation هون بهالرسمة كيف بيصير شكله؟ يعني هلا أنا هون بلشت بالأول قلت لكم assume B is fixed. إذا B منا fixed. بتصير رسمة 3D. بصير عندي B axis. بصير for every combination of WB عندك value for J. مين يفرجيكم كيف شكلها؟ It shows up later on. اوكي بيصير شكل. This is what we were talking about. انه هون بلشت وجراديولي عم بمشي عكس الجريدينت. وهيك بيصير شكله اذا عندي WB، يعني هذا مثلا بيكون البي اكسس، هذا الدبليو اكسس، وهيدي الجي. فبيصير for every W and B combination عندي a specific value for J، والجريدينت بيصير كأنه 2D الجريدينت، مش بس شمال ويمين، بيصير بيأشر anywhere in the plane. اوكي؟ بيصير بدك بس ستيل بتمشي عكس الجريدينت. يعني لاحظوا هون كيف كان الباث تاعولي نازل كنت جالس بعدين كوعت شوي بعدين كوعت شوي. This is kind of normal. Okay? It's not and we would prefer it to not be this way, بس انه it happens. طيب going back to this. Going back to this, I have this model. W hat is Wx plus B, and now we want to expand this a bit. What we've been dealing with so far is one input feature. You give me the number of tourists, I give you the hotel price. You give me the area of a house, I give you its price. You give me X, I give you Y. But usually in machine learning, we have multiple features. We have multiple input values. A feature is an input value, by the way. So how do I deal with all of them?
Vector. نحطهم vector.
بعدين. And how would my model be affected? Storing X is not a problem. I can store X in a vector ما اختلفنا. But how do I deal with them in the context of my model? بصير كل وحده عندها weight separate. صح؟ يعني صار عندي W1 X1 W2 X2 W3 X3 يعني حتصير هيك. حيصير my new model is Y hat is W1 X1 plus W2 X2 plus B. Okay? You just add these. Well, there's a big two plus one. Anyways, you just add these up. فلاحظوا انه الويت تاع الاكس 1 غير الويت تاع الاكس 2. فصار في I can يعني اذا مثلا let's say اكس 2 ما كثير لها عازل. مثلا ما بعرف عندي الاريا اوف ذا هاوس، ما بعرف عدد البلاط اللي فيه. بيطلع عدد البلاط ما له عازي بالسعر. فبيطلع بتلاحظ الويت تاع عدد البلاط بيكون قل كثير. اوكي؟ إذا you have useless features you would hopefully see إنه the weight is decreasing in linear regression. فإذا بتطلع بهيدي الإكسبريشن اللي كتبتها هون، هيدي اللي هون it's as if عندي vector composed of W1 W2 إذا أنا عم بجمعهم لهون صح؟ فكأني عم بعمل dot product لفاكتور اوف ويتس مع فاكتور اوف شو؟ اوف فيتشرز صح؟ بلا 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 فايم getting the dot product بين الفاكتور بين الويت فاكتور والفيتشر فاكتور اوكي؟ فthis is how we usually represent it. y hat is the dot product بين wx plus v. هيدي واضحة للكل؟ انه كيف الترانزيشن تو فاكتورز واضحة؟ dot product بين هول الاثنين what does it mean؟ انه ماشي w1 مع x1 w2 مع x2 ضرب كل وحدة مع اختها واجمعهم. اوكي؟ طيب هلا شو حيتغير باللوس فانكشن؟
السم تبع الديفرنس بين كل
No. حضرت ما هي. This will stay the same. اللي بيتغير هو جوات هي. انه هاي internally صار فيها فاكتورز وعم صرت عم بضرب كثير فيتشرز مع ويتس، بطل بس انه فيتشر مع فاكتور واحد، بس انه from this level انه خلص ما انا شو الانتويشن كان؟ Get your prediction, compare it with the expected result, وsquare it. This doesn't change. صح؟ الكوست فانكشن كمان doesn't change اذا بتطلع فيها بهالشكل. اوكي؟ بس لما اجي اطلع فيها internally وطلع بتفاصيلها this changed. اوكي؟ بس انه the intuition of the cost function remains the same. انه get your prediction وget your وget the expected output نقصهم square وget the average. بعد نفس الانتويشن، اللي فرق بس انه to get my prediction it's slightly different now. صار عندي more features. تمام؟ طيب هلا هون gradient descent becomes يعني it doesn't get more complicated, it becomes notation شوي بتصير مزعجة. بطل عندي W صار عندي WJ the jth weight. بس هذا نفس البروسيس. The jth weight at time t plus 1 is equal to the jth weight at time t minus alpha times the wj component of j. فهمتوها؟ That was a mouthful. البي بعدها نفس الشيء. b t plus 1 is bt minus alpha sigma j del j by del b. والديريفاتيف كمان it becomes a bit يعني بيصير you have to take into consideration بطل عندك w1 فالنوتيشن بتصير شوي مزعجة أكثر. بس إنه the intuitive process is the exact same thing. تمام؟ فكويك ريكاب عملنا weight لكل x we represented this by a dot product. ال ما تغيرت at all. ال j ما تغيرت at all. بس both l و j بيتغيروا إذا بتطلع ب how y hat is being calculated. أوكي؟ طيب. هلا we're gonna talk a bit about okay let's اول شيء لحد هلا في سؤال then we're gonna move on to something else.
بس اول شيء انت بلشت تشرح حطيت سكاتر بلوت وحطيت اللاين اوف بيست فيت وهيك كان عندك اكس وحده هلا بس عندك كذا اكس كيف بتصير؟
اوكي good very good question. كمان بتصير 3D بصير عندي let's say عندي x y z الزد بتصير هي my output x و y هي my input features.
اوكي وبست فيت كيف بتصير؟
line of best fit still.
واحدة بيناتهم كلمة
لاين واحد منه فيهم كلمة. تمام؟ ستيل حتى نطلع لاين اوف بست مش انه حطلع بلين اوف بست فيتنج عم تفكر. لا. اوكي. اكشلي لحظة شوي. بلا بتلاقي بلين اوف بست فيت. بلا. You'd be finding a plane of best fit. انه for every x و y بدك تلاقي some z. بلا you'd find a plane of best. You'd find a plane of best fit عليهم للبوينتس. بلا. اوكي. بس انه good question. The higher the number of dimensions, the more complicated the calculations become. يعني هلا هون بس لانه زدنا number of weights صارت معقده شوي، حتى السميشن تحت صار معقد شوي. This becomes more computationally heavy. يعني تبقوا مثلا هيدي انه اوكي it's like 2 centimeters of rotation بس هي dot product. هودي فيكتورز يكونوا كل واحد بقلبه 1000 element. وعم تعمل dot product this is computationally expensive. ف when you get to very high number of features, مش حتى very, when you get to a reasonably high number of features و reasonably high number of data points, بصير the mathematical method اللي حكينا عنها to find the line أو plane of best fit بتصير كتير computationally expensive. فgradient descent gives you an approximation، وهو إذا بتلاحظوا gradient descent إنه يلا بلشنا randomly وعم بنزل بهالهيل وhopefully نوصل لمحل ما بدي. بس حتى لو it's only an approximation, it's a very good approximation, it's much faster computation. Okay? هذا انه كنت قايل لكم I'm going to talk about why we don't use the mathematical method. طيب هلا this model. This is a linear regression model, W1x1 plus W2x2 plus b. What do x1 and x2 represent? x1 is the length of a plot of land. x2 is the width of the same plot of land يعني. y hat is the predicted price of the plot of land. تمام؟ واضح الموديل شو بيعمل؟ إذا أنا بدي أبعت هالموديل لحدا فيكم I want to share this model with one of you. شو لازم أبعت له؟ W1 W2b. Everything else is not under our control. Our model is W1 W2b. These are our weights. هلا السؤال إذا أنا trying to predict the price of a plot of land. Are my features good features؟ يعني جبت الطول والعرض وعم حطهم بلينير ريجريشن موديل. Are these good features؟
ما بعرف يمكن
إنه
شيء خاص بالعدد.
No, إنه my point is إنه in this context مثلا I would say the area is a better thing to look at.
أنا تسهلها.
صح. What's the area? It's x1 times x2. بس my model doesn't have that capability. My model بس بحق له غير W1 W2b. ما في يجي يضرب x1 ب x2. Okay? So I'm gonna help it. I'm gonna create a new feature هسميها x3 و x3 is gonna be x1 times x2. هفوتها معهم هالخبيصة. تمام؟ صار عندي W1 x1 W2 x2 W3 x3 plus b. وهون I'm writing it in expanded form لتعرف انه x3 انه اذا بتطلع بالموديل بالنسبه للموديل x3 مثل حيلا فيتشر خلص I'm training الدبليو عم بعمل gradient descent وحرك الدبليو شوي وما بعرف شو مثل حيلا فيتشر بس بالنسبه لنا we know انه x3 is the area. The feature what we just did is called feature engineering. Feature engineering is taking a bunch of features and then creating new features out of them. Well, these new features would usually be more useful, more representative of my label. مثلا in this case اخذنا x1 x2 وحولناهم x1 x2 و x1 x2. يمكن يجي حدا يقول لا انا I want to remove x2. In some cases تشيل الفيتشرز اللي قدام تترك بس الجدال او تخلي شوي من القدام او تزيد الجدال. The main principle is we're pre-processing the data set. يعني عم نعمل شيء قبل التريننج. This happens before we start training. And we transform our data into a more effective data set. شو يعني more effective؟ إنه the relationship بين the label and the input features is stronger. يعني the relationship between the price and length ما حتكون قوية قد the relationship بين the price والاريا. صح؟ طيب مثلا إذا عندي هيك data set. I've plotted it x مع y وهيك شكله. اوكي؟ إذا بيجي بعمل I try to find the line of best fit على هيدي، شو حيطلع معي؟ بيطلع لاين تعيس. This is not linear. طيب what would you suggest we do? I can يعني تذكروا أنا هلا صار I can play around with my features. هون عندي feature واحدة اللي هي الأكس. شو في أعمل؟
كوادرات x سكوير
100% زيد فيتشر جديد يسميها x2 و x2 بتكون x1 سكوير. صار ماي موديل W1 x2 زائد W2 x1 اللي هي الحقيقة W1 x1 سكوير زائد W2 x1. واضح؟ اللي بفكر نعم؟
هيدي بعد اللينير لا
هلا هو ليك شو؟
هي x2a بس هي x1
100% بالنسبة للموديل the process is the exact same.
بس
بس انه لا هيدي ما عادش نسميها linear regression لانه in reality we know this is not linear. هيدي بنصير نسميها polynomial regression. اوكي؟ بس اذا عندي هيك شيء هون I can fit radical x مثلا. فبزيد W1 radical x1 زائد W2 x1 زائد b. اوكي؟
بس سؤال ليش بيجيبوا طالما زدت راديكال ليش هذيك التانيين بيجيبوا W2 x1؟
انت حر، فيك تتركهم فيك تشيل. فهمت كيف؟ in this case حسينا انه لا في ريليشن شيب بين الواي هات والاكس 1 بس انه هيدي مهمه بس انه ستيل في ريليشن شيب هون فترك.
ما بتأثر يعني؟
مش ما بتاثر، هيدي حسب يور سبيسيفيك كيس. ممكن يجي يعني السبيسيفيك كيس ممكن اقول لك شيلها، السبيسيفيك كيس كمان انا اقول لك تحطها. فهمت كيف؟ مش انه it's not personal preference. نفس الشخص in different situations might do different things. ممكن يجرب الاثنين. تقول لي خليني اجرب تركه وجرب حطها وشوف اي بيعطي ريزلت احسن. فهمت كيف؟ this is dependent on انه الواي هات على شو بتعتمد. تمام؟ بس عند اكزامبل البيت اذا عندك صح اذا الاريا كبيره انه this is more important than price، بس كمان اذا اريا كبيره ومثلا وقت كثير صغير كمان this is important to note. طيب this is one type of feature engineering اللي هو انه it gave us polynomial regression, it gave us radical x, it gave us the area. this is a very powerful tool. هلا حنشوف another type of feature engineering. let's say عندي هيدا الموديل. I don't care what the actual what this represents. x1 is between 10 and 70. x2 is between 30,000 and 100,000. Okay? مثلا let's say this is age ما بعرف income per year شو بعرف فيه. هون who can predict a problem based on الاشياء اللي هلا حاططها هون؟ شو في مشكلة معقولة نفوت فيها؟ صح. What can this cause؟ إذا كثير في فرق بين الرينجز هيدا ممكن it can cause us إنه one feature dominates the other features. صح؟ إنه صار هلا الإكس 2 فعليا هي اللي عم تتحكم بالواي هات مش الإكس 1 يعني إكس 1 contribution تبعه كثير قليل in comparison.
هذا الشيء هو بيبين ب W2 إنه بتكون مثبتة.
That's a good observation. بلا W2 in this case W2 would naturally become smaller. بس هلا حنشوف شو I'm gonna get to what you're saying basically. Okay? هلا هون x2 is much more dominant than x1. فصح W2 is gonna try to compensate. بس this compensation makes gradient descent less efficient. يعني إذا بيجي بتطلع بهيدي. This puts it very well. هلا اللي عم بتطلع عليه انا بس لحتى to define our graph. عندي W1 و W2. اوكي؟ W1 و W2 they're my two weights. البايس for now كان I'm ignoring it. وعندي Z axis اللي هو الجي. اوكي؟ هلا انا ما عم I'm not graphing الجي I'm not graphing الجي in 3D. عم باخذ الكونتور تاعه. Do you remember what that is? basically عم باخذ انه for j equal to 2 هلا for j equal to 1 هيك شكله for j equal to 3 هلا شكله اتسكر. اوكي؟ هلا هون I know انه شكلها هيك حيكون الجي. هون شكلها مثل هالرسمه. اللي على اليمين. اوكي؟ فبيسكلي I'm taking slices. فانا عم بنزل بجريدينت ديسنت حانقل من سلايس لسلايس. ما هيك؟ This is how gradient descent would look like in such a case. بما انه the way this is shaped مثل كأنه stretched أو oval اللي بيصير إنه the way the gradient will point will make me overcompensate. يعني the gradient will point in this direction أنا حروح too much على اليمين بعدين too much على الشمال too much على اليمين too much على الشمال حكون عم بوصل للمينيمم بشكل زجزاج. أوكي؟ بينما لو كان شكله هيك circular بنزل تقريبا straight to the minimum. Is this making sense? يعني إذا أنت actually هذا demo for this بس ما معي إياه هلا إنه إذا you go through the intuition at this point the direction of greatest increase هي هيك بينما the direction of decrease حتكون بالعكس بس إذا بتنزل هيك ما حتكون عم تنزل straight towards the center حتكون عم بتزيح ف you're doing a lot of unnecessary movement. تمام؟ بس لأنه بس لأنه W1 versus W2 is squished.
مش usually we used to do the gradient descent على J versus W.
صح this is still J versus the W's بس J هي third dimension اللي عم بعمله انا بدل ما ارسم third dimension بس انه for to explain this idea I don't care about the third dimension اوكي فاللي عملته انه اخذت لهاي I just took slices اوكي طيب فاحنا بلشين هون عم نمشي in a zigzag fashion this is a problem okay can we agree that this is a problem هون it would be a bit more straight to the center طيب هلا فاذا how do we solve this فينا simply to scale the features بدل ما هيدي تكون بين 10 و 70 وهيدي بين 30k و 100k عملنا اثنيناتهم بين 0 و 1 كيف عملنا اثنيناتهم بين 0 و 1 normalize 100% you either في كذا طريقه to do this اول طريقه انه for every feature اقسمها على maximum value يعني اذا انا عندي data set I know انه x1 is between 10 and 70 اقسم كل شيء على 70 بتصير بين 0 و 1 مثلا فينا لا نقصها من المين واقسم على الرينج whatever the point is normalize it ما ضروري تكون بين 0 و 1 مثلا في عندك z-score normalization which is a statistical method this is basically إذا ماخذين stat to 30 you either saw this or you will see it it's basically another type of normalization ما بتحطهم بين 0 و 1 بس كمان it squishes them around 0 but the point is just squish everything اللي يصير على بعضه and then you get something like the one on the right you run gradient descent on this it's much more like it runs beautifully on that but then بتكون running in this ugly fashion هون تمام؟ اوكي هلا حابب نحكي شوي عن learning rate how the learning rate affects the convergence of J اول شيء هيدي الكيرف اللي عم نرسمها هون كل وحده من هون بنسميها learning curve what's the learning curve هي الكيرف that corresponds to the number of iterations versus J يعني كل ما I train my model أكثر what do I expect يصير بالJ؟ إنها تقل صح؟ ف this is what the learning curve should represent إذا عندي a very small value of alpha حتكون ال learning curve عم تشتغل صح اوكي حيكون كل ما increase كل ما there's more iterations حتبلش تنزل my point gradually اوكي بس لاحظوا انه it's gonna take a very long time يعني حضلني انزل بس انه I'm plateauing at a high value اوكي it takes a lot of iterations لحتى لاقي my actual min يعني حتحرك من هون لهون 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 it's gonna be very slow اوكي as I set a value of alpha that's good I will have the same behavior but much faster this is what we aim for إذا عندي alpha that's very large يمكن لاقي الجي بلشت تطلع لأنه خلص صرت شو يعني alpha is very large أنت كنت هون وطلت نطة كبير نطت نطة كبير بلشت عم you're skipping the minimum تمام؟ أو ممكن لا إنه عم بنزل maybe بس إنه I'm oscillating this is bad this is bad we aim for this okay a few things that we're going to talk about is how we actually train our models to train our models the process goes as follows عندي data set باخدها I split it into two parts my training set and my testing set okay what does this mean انه لما انت تيجي عم تدرس الامتحان you don't ما بتقرا يعني ما بتروح بتحل الاسئله كلها انه اوكي let's say البروفيسور حل كم example you would walk through the examples مع البروفيسور مش بتحلها انت لحالك maybe this is your style of study انه ما بتحل الاكزامبلز لحالك تمشي معه للبروفيسور بس at the end of the day you need something to test yourself صح this is where the learning actually this is where the testing happens this is where the learning happens we do the same thing in machine learning عندي my data set I split it usually around 80% of it هلا هودي الارقام you can choose مثلا 70% او 50% whatever بس انه let's say 80% of it you feed it into your algorithm نحن in our case this is linear regression او polynomial regression and then you get a machine learning model هيدا الموديل you test it using the testing set you evaluate it based on that أنا بحكي عن evaluation at some point okay الموديل can be in one of three states generally يا اما it underfits our data يعني our data looks like this but my model is a straight line this is underfitting تمام او my model looks like this بس my model يعني عم يمرق على كل نقطة عم بيسيبها. This is overfitting. يعني not only are you fitting to the points, you're fitting to the noise كمان. تمام؟ This is what a good model looks like. It's a good generalization. لا too underfitting ولا too overfitting. تمام؟ Okay. The way we get here is by playing around with alpha or by playing around with other parameters. Actually, regularization I wanted to talk about, بس بحس we've had enough for today. Let's keep this for next time. خلاص خلصنا for today. يلا يعطيكم العافية.